Hello, my name is Abisha Bangana, and I'm going to be taking you through the machine learning course with Python, and basically going to be talking about the modules that I learned from the Alison course. So this is an overview of the 7 modules, and as well as the problem and solution that I propose to the problem that I identified and how I believe it can be solved using machine learning. So module 1, we are looking at introduction to machine learning. What is machine learning? So this is basically a field of study that gives computers the ability to learn without being explicitly programmed. And we have 2 types of machine learning: supervised, which works with labeled datasets, and then we have unsupervised machine learning, which works with unlabeled datasets. And here, the machine learning model has to identify hidden patterns and structures within the data. For example, clustering or anomaly detection. Moving on to models. A model is a representation of some phenomenon, and we have the math or statistics models as well as the probabilistic models. Math models have 2 types. We have deterministic, which includes no randomness, and then you have probabilistic models with randomness. Then probabilistic models have 3 types. We have regression models, which are used to represent the relationship between one dependent variable and an explanatory variable. Then we have correlation models as well as other models. Moving on to module 2, which is key nearest neighbors, or what we call KNN. We are going to look at parametric models as well as non-parametric models. In a parametric model, you know which model exactly you will fit to the data, whereas in a non-parametric model, the data tells you what the regression should look like. Then moving on to the distance, we have Euclidean and Manhattan. Euclidean is used when the dimensions measure similar properties, whereas Manhattan, it's dealing with dissimilar properties. Then KNN has 3 main algorithm steps, and that is calculating the distance between the training data and the test point, finding nearest k-neighbors by sorting their pairwise distances, classifying the point based on a majority vote, and some of the main KNN applications are text mining, agriculture, finance, and cargo competitions. And another thing to take note of when we are working with hyperparameters in KNN is that you should never tune them using the test data. Moving on to module 3, we look at decision trees. And in decision trees, we have what we call the Gini impurity, which measures the frequency at which any element of the data set will be mislabeled when randomly labeled. Then the Gini index is faster because its interval range of values is lower, which is 0 to 0.5, whereas entropy is higher since it's 0 to 1, which makes it more complex since it makes use of logs. Then we have what we call information gain, and with information gain, we have to know that it's biased for attributes that have many outcomes. Then moving on to the pros and cons of decision trees. The pros, one of the pros is that it's easy to interpret and visualize. It has no assumptions about data distribution. It can easily capture nonlinear patterns and can be used for feature engineering. Whereas the cons, it's sensitive to noisy data, and it's biased with imbalanced datasets. Moving on to the 5th module, which was Ensemble Learning and Random Forests. We have to know what Ensemble Learning is, and this is a machine learning technique that combines many mediocre models to come up with one supermodel that is able to improve predictive performance and accuracy, which a single model cannot do. Ensemble learning has 3 major techniques, which is bagging, boosting, and stacking. Bagging versus boosting, whereas boosting is a sequential tree growing with weighted samples. Bagging is instead a parallel tree that grows with subsamples. Then moving on to stacking, this involves training multiple different models and then using the predictions as inputs to a final model. Then what is a random forest? This is a slightly modified bagging algorithm, and it's basically a collection of decisions of decorrelated decision trees. So we have to know that for every tree, we randomly pick features in each split. For each subsample, we choose attributes at random. We subsample the examples with replacement bootstrapping, and we build the tree only on these random features with the current subsample. Then with random forests, with random forests, we have the same pros and cons. So with pros, it's robust to outliers. It works with nonlinear data, lowers the risk of overfitting, and it runs efficiently on a large database. Whereas the cons, it's biased while dealing with categorical variables, slow training, it's slow to train, and it's not suitable for linear methods with a lot of sparse features. So our sixth module, we are going to look at SVM, or what we call the support vector machines. And in here, we are going to look at clustering, k-means, and the pros and the strengths and weaknesses of k-means. So I would say ideally SVM, it gives more weight to correct classification than margin maximization. And SVM can detect outliers and also ignore them. Then we have gamma. Gamma is a hyperparameter for SVM, and it controls the distance of influence over a single training point. Then k-means, some of the strengths are it's simple and easy to understand and implement. It's a linear algorithm, and it's the most popular clustering algorithm. Whereas the weaknesses, the k-means algorithm is sensitive to initial seeds, and it's not suitable for discovering clusters that are not hyperspheres. Then what is cluttering? Cluttering is a technique for finding similarity groups in data, which are called clusters, and it's often called an unsupervised learning task. And our last module that we're going to be looking at today is the principal component analysis, or what you can call the PCA. And its goal is to reduce dimensionality of the data while keeping the information loss to a minimum. It performs lossy compression in that the information that is information is lost when we discard insignificant components. And you should not adjust scaling to match prior knowledge of data. This is because scaling can yield different results, hence the scaling that you use should be documented. Main applications of PCA include image comprehension, data visualization, facial recognition, and pre-processing or classification. So these are some of the key algorithms that are in machine learning. We have regression models, we have decision trees, classification techniques such as KNN, which is key nearest neighbors, and SVM, which we've also looked at. We have neural networks and deep learning, as well as clustering methods such as k-means. Then the problem that I identified, which we are going to break down, is what is the problem? And our problem today is a socially engineered transactional mobile money fraud in Uganda. And what we are looking at is not just hacking, but a mix of SIM swapping, provider impersonation, as well as split agent deposits, whereby the thieves break down the stolen money and distribute it differently in order to avoid detection. Why is it a problem? So this is a problem because with Ugandan mobile money systems, they currently rely heavily on static pins and human monitoring. Therefore, if a fraudster is able to get the pin through like a fake phone call, the system thinks that that is the actual person. To whom is it a problem? So here we are looking at the affected party, and we have small businesses, we have the Uganda economy, and we also have the rural or uneducated population. It is a problem to the economy because Uganda loses over like 18 billion as seen from the UCC reports to mobile money fraud, which slows down financial inclusion. To what extent is it a problem? It breeds mistrust. And recent reports show that with the mobile money usage in Uganda, as it has gone up by over 166%, nearly 47% of the users have at least one fraud attempt. How is it a problem? Mobile money fraud is adaptive in that when the government passes a misuse act, fraudsters just change their script, and rules cannot keep up with scripts. Therefore, there is need for a machine learning model that learns the behavior of the thief and not just their PIN. So this is the proposed solution, which is a multi-layered intelligence solution. And we have three main layers. We have layer one, which is geointelligence, which looks at where the transaction has taken place from. Then moving on to layer two, we look at natural language processing and behavioral metadata, which is the what is taking place. For example, it scans for social engineering keywords such as bonus price, detects instructional latency, the pauses that would happen when a user is being coached over the phone by the fraudster. And our third layer is the probabilistic risk scoring, or what we call the action. And here, this is what the system is basically going to do. The feature is that it's going to have a logistic regression output that's converted to a risk percentile. And the solution, instead of a simple block, the system triggers adaptive authentication based on the risk level. So these are some of the key takeaways as we shift from rules to behavior, since the rules cannot actually stop the fraud from happening. And we have our multimodal intelligence solution, which is going to combine geointelligence for location, NLP, or what we call natural language processing for text analysis and behavioral sensing, or the user speed to create a behavioral firewall, which is much harder for fraudsters to bypass. Then we have adaptive authentication, where we use risk scoring. Then we shall have Python as the engine of integrity, and trust is the ultimate goal, in that machine learning in mobile money isn't just about saving money, it's about restoring trust in Uganda's digital economy. Thank you.